Welcome to the stream, nerds. We're going to continue our frequency response. Kind of a continuation from the last stream. We're going to be working with the same circuit parameters, such as like the resistance values and the capacitance values, and I'm going to draw it out for you. And then we're going to do the analysis together. So we're going to have a capacitor here in series with this resistor. Be in series with this parallel circuit here. Okay, and we're taking the output, bada bing, that's the positive of the output. This here is connected to the inverting input of our operational amplifier. That's just another component. It's an integrated circuit, operational amplifier. Yeah, to describe it as an integrated circuit is like a very general description. Specifically, it is an operational amplifier. And then even then, there are many different kinds of operational amplifiers. Positive, negative, V, in. Okay, and now we have a complex input. We have a complex output to do a frequency response. It's like a typical circuit, right? This is what the actual components look like in a schematic or in a circuit diagram. But, you know, I guess we go about drawing it, modeling it differently when we're doing impedance values. And so I'll give you some insight into what this looks like. Alright, so it's really just like the very same thing, except we draw things as boxes. We describe them by their impedances. Capacitor with subscript 4. Instead of seeing C3 or C4, we're going to put it into its impedance form, which the impedance for a capacitor is this 1 over C3S. And where S equals, make sure you can see that, J omega. And so to convert frequency into angular frequency, this omega here, you just multiply the frequency by 2 pi. For 1 over C4 times S, where S equals this imaginary number J, which is J equals, so we'll just write all this out, equals the square root of -1, right? That's your imaginary numbers. If you have J squared, then it itself is going to be -1. Right. This time, the frequency breakpoint specifications are the same, which was 10 hertz on the low end, 20 kilohertz on the high end. But we don't have enough degrees of freedom to independently specify the midband gain. Okay, so let's put down our knowns. I don't know exactly where it's applicable, but we have a 220 picofarad capacitor, resistors to pull from within a range of 100 to 100 kilo ohms. That's break. Free. Beautiful. You like that? Okay. So this is what we're working with right here. Okay, so we know that our break frequency is determined by this inverse of tau. This all makes sense, where tau itself equals, in this scenario where we have just capacitors and resistors, it's RC. Transient analysis, we're doing the frequency responses, right? So this doesn't have anything to do with time dependency. It's more like we consider it to be steady state. Okay, so it's honestly such a beautiful feeling when you've been struggling with something and then you persevere and you overcome the challenge. You know, it brings a sense of accomplishment, a sense of success. But this right here, this is what I want to know. Filters. With a parallel capacitor with the series resistor, we can achieve the desired voltage divider at high frequencies. Indeed. Alright, let's just jump into it. Let's just start V negative minus VI. Okay, divided by the combination of 1 over C3S plus R3. There is a very minute amount of current that flows into the operational amplifier inputs, but it's so minute that it's negligible in reference or like in comparison to any other current flowing in the circuit. V positive itself is 0 right now, and in an ideal operational amplifier, the loop gain A, which is just one of the parameters of an operational amplifier, in an ideal op amp equals infinity, therefore making V positive approximately equal to V negative. This is what it's actually going to look like. It's going to be 1 over Okay, so it's gonna be R4 times C4S plus 1, and then R4 is gonna go on top. So I'm gonna go ahead and say that. So now we're actually going to have, and I'm gonna put that on that side. All right, so we're gonna make everything positive. VI C3S over 1 plus. Yeah, that's the thing though. That's not necessary. Imaginary or complex very forward. So we'll move everything over as we need to. VI R4 C3S divided by. Okay, now all this equals V out. I want to convert these complex variables right here, and I'll convert it into the real. Okay, add it up here. So negative VI R4 C4 times omega. This right here, this one's gonna come down to this. And now square root, we're gonna come over here, we're gonna say that's gonna be all multiplied by the square root of, which is this. Just like that. To denote the magnitude, we no longer have a complex variable, but we have the magnitude of a complex variable. And that's a bar. Okay, so now this is the real component of our complex variable, of our complex input, our complex output. This is the real component of it. So now what I could do, we still have our break frequencies. Recalling from the last stream or the last problem that we worked on, it was 10, 6, 10, and it was 36171. Shit. 36171, that is right. Okay, 3617. So this is, continuing from the last problem. These are values of our resistors. And now this is R3. R3 equals, this equals R4. Okay, so that means C3 equals, here, I'm gonna get rid of this. That was not applicable. That was a dumb route. C3 equals 1.5 microfarads, and then C4 equals 220 picofarads. Okay, now what is the mid-band gain for this circuit? The mid-band gain. Okay, last time we want the mid-band, we wanted a gain of 2 at the mid-band frequency around 1000 hertz, 1 kilohertz. Again, to get our omega, 1000 hertz times 2 pi is going to give us our angular frequency, which is like 6,000 something. 1000 times 2 times pi. Okay, so you can see that. Boom. 6283 be radians per second if we want to apply some units to our angular frequency. This is what we're going to plug in now for this omega here. We're going to see the outcome for some like arbitrary value of Vn, which means I'm going to pick it. I'm just going to pick a random value of Vn and see what V out is. So I'm just going to go with 5 volts. Okay, so this is what we're going to do. Okay, we know what R4 is. We know all of our shit now. Okay, so 36171, whoops, 6283 times our negative 5. Whatever, we didn't need the negative really. Okay, we get a real small number. We're going to do this. We're going to go the square root of 1. R3 106. All right, let me run the calculation back just one more time. How about this? Yeah, let's do this a bit differently. R3 plus 1 times both of those, so I'm gonna do that. All right, ladies and gentlemen. Okay, 1 minus. So this is gonna change. Man, this changes quite a bit. Now this is what we'll use, and we'll plug in 6283 again. Ah, man. Really? Alright. What is the mid-band gain? Let me explore another route, right? Because we got to this point. So R3, R4, C3, C4. Okay, so now this variable right here in particular, let me just do a calculation and see what that comes. I guess that's maybe where I messed up. All right, so we can say that so before I just put C4 and R4 in parallel. Now I put it in a way that I considered the current going through each of them individually rather than both of them as a whole. But I don't know if that's really going to make much of a difference. Equal. Alright, because we got that over that. That's going to go in the numerator just like that. So we have that V out equals C3S in the numerators or C4 S. We actually had been R4 multiplied by C3, not C4. C3. Okay. So look at the difference. This is the appropriate calculation. Look at 1,704 is 220 e to the negative 12 times 6283. Look at how much smaller that is. Okay, so now let's carry on with the appropriate value divided by, and we can use this because these two got us the same answer. 10 times 1.5 e to the negative 6 times 6283 squared. 17. Okay. Our output voltage with the correct variable in place is 17 volts from 5 volts. 17 divided by 5, 3.4. Our mid-band gain is 3.4. I don't think our gain equals V out over V in. Okay, magnitudes. And so that's just going to equivalent to this. Get rid of that. Negative R4 C4. It's just going to be this function here, and then now we plug in our values for that, and we get a gain of negative 3.405. Yeah. Man, I create more problems for myself than necessary by not paying attention to detail. So let me work on that. And you guys work on liking the video and following me. All right.